Hello, this is Mr. Collier, and today we're going to do some optimization problems. So in this problem, square corners are cut from a 12 by 12 tin plate, which is then bent to form an open dish. What size square should be removed if the volume is to be a maximum? So what we have is we have a square tin plate, that's 12 by 12, and we're cutting square corners, and then you can make a 3D open dish after you cut out these corners, and you can fold these sides together and make it like a rectangular prism dish. Alright, so what size does this need to be to maximize the area? I'm going to call that X because we don't know that size. That's going to be our variable. That's the same right across the board here. They're all X. So we want to maximize the volume, so we need a formula for the volume. Now when we fold this together into, I'm going to try to draw the box that we'll get. Okay, we're going to have a box like this once you fold all that together, and this is going to be X, and so that dimension is X. Now think about this side right here. This side comes from these, right? These are all the same. They're not 12, they're less than 12. This distance here is 12. Okay, so this distance here, we have two x's on the end, so this is going to be 12 minus 2x. Alright, so that's 12 minus 2x, and this is 12 minus 2x. So to get the volume, we're going to have volume equals x times 12 minus 2x times 12 minus 2x. Alright, and we can maximize this. You can simplify this and find the derivative and find the maximum and all that. I'm going to try graphing it, see if that's going to be any easier. So I'll graph it, and I'll get, let's see, let's type it out as it is, x times 12 minus 2x, and then 12 minus 2x. Or I could have done 12 minus 2x all squared, same thing. Okay, so I'm going to graph that. Now if I do zoom 6, I probably won't see much. Right? Oh, I can see a bit. The maximum volume is going to be a lot bigger. So let me just change my Y max. Let's say this gets up to about 100 or so. This is just a kind of a guess. Okay, so we can kind of see we're getting a bit higher there. So I'm going to go up to 150. Let's try that. So now I can see much of the function. Now obviously x can't be, maybe I should write this in here. The maximum that x could be is up to 6, right? You can't get any more than 6. So x is going to have to be less than 6 for sure. Probably a lot less than 6. So one thing I could do with my window here is I can change now the x min. Of course, the minimum possible x value is 0. Maximum is 6. So maybe this will give me a bit of a better picture. And it does. So if I just look at this interval right here, I can see the maximum occurs right here. Okay, we can find that on our calculator. We can find it by hand by getting the derivative. But let's just try this calculator method first. So I'll do second function trace, and it is a maximum, so I'll press number 4, and then to find the maximum I'll go to the left of that turning point, or stationary point if you like, to the right, and guess right on there. It's at, now the calculator gives you 1.9999 whatever, That's very, very close to 2. It should be exactly 2. Actually, your calculator is just estimating. So that point is 2, 128. Let me draw a sketch. Okay, that point is 2, 128. So in conclusion, you can say when the square is 2 centimeters, okay, that's where I got the 2 centimeters from, the volume is maximized, perhaps you could say, or optimized, maximized, and the volume is 128 cubic centimeters when x is 2 centimeters. Okay, so we did all that using the calculator. Let me just show you, because sometimes you might have to do this by getting the derivative as well, right? So the function, the volume is, if I simplify here, I'll get 12x minus 2x squared times 12 minus 2x, and that equals, 12 times 12 is 144x minus 24x squared minus 24x squared plus 4x cubed, which is 144x minus 48x squared plus 4x cubed. To find the derivative, dv by dx is going to be 144 minus 96x plus 12x squared. So you can solve that for 0, for that equal to 0 to find the stationary point, right? You use polysmalt. So you could say, yeah, by polysmalt smalt 2, and I'm not going to go through that. I know the answer already is going to be x equals 2. If you use polysmalt, you can verify that. You get x equals 2, and yeah, that's the answer to the question. The square size needs to be 2 centimeters. Okay, so you did it by the calculator or by finding the derivative. Next problem, find the minimum surface area of a cylinder which has volume 330 cubic centimeters. So first you need to look up the surface area of a cylinder, formula for that. So surface area, I'll just call it S, I guess. Surface area equals, for a cylinder you have 2 pi r h plus 2 pi r squared is the volume of a cylinder. We've got 2 variables in there right now, but you want just one variable, so you have to find a way to write that as one variable. So we have a cylinder, and we have a rate. So we have the volume is 330 cubic centimeters. So we'll start with that. Volume equals, for a cylinder, is pi r squared times the height. And they give us that's 330 cubic centimeters. So 330 equals, yeah, pi r squared times the height. So the easiest thing to do here is to solve for h. Alright, h is a bit better to solve for than r because you have 2 r's here. It's going to make it a bit more complicated. So if I solve for h, I get 330 divided by pi r squared. So that's the height. I can take that and substitute it into the equation for surface area. And then I'll have one variable. So all this we just did to get a formula for surface area with one variable. So we have 2 pi r times 330 divided by pi r squared plus 2 pi r squared. So it looks a bit complicated, but we have one variable. So that's going to make it a lot easier to solve this problem. I can simplify a little bit. It's not totally necessary, but 2 times that is 660. Pi's cancel, and r squared becomes r. Well, that cancels, and I just get r to the power of 1 down here. So 660 out of r plus 2 pi r squared. So you can find the derivative and all that, or if they don't tell you to find the derivative, you can use your calculator again. and type in this function. So 660 divided by x plus 2 second function pi, or r squared, well x squared in this case. So there's the function. Now I could try zoom 6, but usually you don't get to see anything with that, so yeah. Well, we know that the radius obviously has to be greater than 0, so I'll put 0 in for the x-min, and my y, I guess my y max has to be a lot higher. I guess the y min has to be at least 0. So y in this case is the surface area. I guess this might be in the hundreds. So let's try 500 for y max. See what happens. Okay, so now we can actually see where the minimum occurs. It's right there. So if we want to minimize the surface area, we have to find that point. Okay, so we're going to do second function trace, and number 3 is the minimum. And I'm going to go to the left and press enter, go to the right, enter, go right on there and press enter. So that is x equals, now the question asks us for the minimum surface area. So when the radius is 3.75 or 74, we have the minimum surface area, but it's asking you for what is the surface area, so we need this one here, 264 square centimeters. Okay, so yeah, we could say now that minimum surface area is, what did I say that was again? 264 square centimeters. I can show the work by simply making a diagram of the function and showing that this point here is 3.74 comma 264.